So we just ran through a bunch of different hypothetical data sets, and I'm guessing that at a certain point you felt like you couldn't believe the mayor of Biotown anymore when he or she was saying that Biotown is 50% men and 50% women. At a certain point, that just feels like not a believable claim, right? So if you went around and did like more than just polling our class, but instead you were polling a whole bunch of people, you'd get a range of answers, right? I think most people would say that if Biotown was actually 50% men and 50% women, and you did your little experiment where you sampled 20 people, that for sure, obviously 10 men, 10 women is great. Most people would say even if it was 11 men and 9 women, that would probably be fine too. 12 and 8, probably okay. But then as soon as you start getting into the 13 and 7 or the 14 and 6, people start feeling less and less confident that they can actually believe that the town is 50-50, right? It starts feeling less believable. But the exact point at which people are not willing to accept that claim anymore is different. And there's also tends to not be a good reason for why. Like, why is it now at this point you aren't comfortable with that claim anymore? Instead, it's kind of just like a feeling, like a gut feeling that just doesn't seem right. And obviously, the problem is if we're trying to evaluate data sets and any sort of evidence that we might collect, objectively, we can't just say, oh, you can't publish a paper and say, like, and my gut feeling said that this didn't make sense. We need something a little bit more analytical, a little bit more robust. So chi-squared test comes to the rescue. So this is what this whole lesson is actually about. It looks like an X, but it's actually a Greek letter pronounced chi. So when you see something written out like this, it's called a chi-squared test. So what does this chi-squared test let us do? Basically, a chi-squared test tells us or lets us think about the amount of variability that there is in the world and basically how that variability is going to impact the actual data that we collect. So even everyone knows, like, if you flip a coin, the probability of heads and the probability of tails is 50-50, or at least it should be if the coin is like a normal, regular coin. But if you actually flip a coin 10 times, you probably aren't going to get exactly 5 heads and 5 tails. Or maybe you will, but if you got 6 heads and 4 tails, that would be normal, right? There's just like variability in your data. So the same thing is going to happen when we're collecting actual data out in the world. There's going to be variability. So the chi-squared test tells us how the actual data that we collected compares to some data that we expected to get. So 50% heads, 50% tails, or 50% men and 50% women in our Biotown example. So this idea of data that we expect to get brings us to a corresponding idea that is really integral to understanding a chi-squared test. And that idea is this idea of a null hypothesis. So specifically in the context of a chi-squared test, a null hypothesis, we're going to use a working definition of being a claim that leads to a specific prediction, and that specific part is important. So you might be thinking about the video that you had to watch before where we were talking about what a hypothesis is and isn't, and I told you that a hypothesis is either an explanation about why things are the way they are in nature, or a claim about patterns that exist in nature, or about just like the way things are. And so in this case, our null hypothesis is a claim, so that squares up, but it's a specific kind of claim that lets us make exact predictions about data that we're going to get. So, for example, with the coin flipping example, if we say that our claim is that it's a 50% chance of heads and a 50% tails, 50% chance of tails, then if we flipped the coin 100 times, we would be able to specifically predict that we would get heads exactly 50 times and we would get tails exactly 50 times. if we flipped that coin 1,000 times, we would be able to predict that we would get heads exactly 500 times and tails exactly 500 times. So if we're making a hypothesis that says this is a rigged coin and we're going to get heads more often than we get tails, and that was all we said, that is a hypothesis. That is like, in just the most general sense of the word, that is a hypothesis that's valid. But it can't be a null hypothesis because it doesn't let us make specific predictions about our outcomes. So yes, we would maybe get more tails or more heads than tails, but we need to be able to say exactly how many heads and exactly how many tails in order for it to be a good null hypothesis. So instead, we could maybe say the proportions of heads and tails that this coin results in is 70% heads, 30% tails. That would be acceptable. So a null hypothesis is a more specific kind of hypothesis than just the general idea of hypothesis we talked about earlier. It needs to give us specific predictions about numbers that we're going to get. Okay, hopefully that made sense. Going back to our Biotown example, our null hypothesis was the claim that the mayor made, which is that Biotown is 50-50 men and women. And that lets us make a corresponding specific prediction about our mini study where we sampled 20 citizens. And so if that claim is true and we sampled 20 people, we should get 10 men and 10 women, right? Okay, hopefully so far so good. If we actually did that experiment, actually did that study, sampled 20 people, let's say that we actually got the results 13 men and 7 women. I know we just ran through a bunch of like hypothetical results we could have gotten. Let's say this is the actual data that we collected, 13 men and 7 women. So we can use the chi-squared test to tell us how likely is it that, given that we got this result, 13 men and 7 women, how likely is it that that's just because of variation in the population and it still is like fitting with our 50-50 hypothesis? Like, does that do our data jive with that hypothesis, or does it seem really unlikely? That's what we're going to be figuring out. Okay, so here's the actual formula for figuring out our chi-squared value. Depending on your level of math comfortability with wordy formulas, this might look scary or not to you, but we're going to break it down real slowly, so it's really not that bad. This first part is, remember we said that x is the Greek letter chi, and it's squared, so this is our chi-squared value. This is what we're actually trying to figure out. And to figure out our chi-squared value, we're going to be taking the sum of some other values. So this yellow figure here is the symbol for summing, so we're going to be adding some things together. And the things that we're adding together is going to be based on what we actually observed. So this is our actual data that we actually collected. And from that, we're going to subtract the data that we expected to get. So this is our predicted data. We're going to take all of that and square it and divide it by our expected data again. So this is all well and good, but it's kind of confusing unless we look at an actual example. So this will make more sense. If it's confusing, let us go through an example and I think it'll feel more clear. Okay, so when you're actually doing a chi-squared test, I think it's easiest to set up your data in a table like this, where you have your categories on the side here. So our two categories are men and women. And then we have all of the components of a chi-squared test or figuring out a chi-squared value across the top here. And we'll run through the steps that you have to take to fill out this table. Okay, so the first column is just what you actually got in your study. So this is just like your actual results, what you actually counted, 13 men, 7 women. So I have faith that you guys can all fill out this observed column since it's just it's counting, which I think you guys can all do. The next step to figure out the rest of the table is first to figure out what your sample size is. So in our example, we were counting up 20 citizens, 20 people. So our sample size is 20 people. If you have trouble with your short-term memory and you forgot that that's what our sample size was, you can also figure this out by adding up the number of people that you actually observed. So if there were 13 men and 7 women, that's a total of 20 people. So your sample size is 20. From that, you have to, I'm going to move this, it's in the way. Sorry. It's really delayed, so it looks like it's not working for me, and then it actually is. Okay, let's just go over here. We're going to use that sample size and our null hypothesis to figure out our expected values. So remember, our null hypothesis is that we have 50-50 men and women in Biotown, and we have 20 people total. So that gives us expected values of 10 men and 10 women. If our sample size had been 100, then our expected values would be 50 and 50, right? So you need both of those pieces of information to figure out this expected column. And then the rest of this table is just math. That's hopefully not too bad. So the rest of the calculations, you're just taking the observed number and subtracting the expected. So 13 minus 10 is 3, 7 minus 10 is -3, and then you're taking this number and squaring it. And that's going to get rid of any negative numbers that you might have ended up with and bring everything to be a nice positive number. So 3 squared is 9, and -3 squared is also 9. So we have 2 9s in this column. And then finally, the last step is to take this number and divide it by our expected value. So we go back over to this expected column, and we're going to take 9 divided by 10. And that's going to be true for both the men row and the women row. So 9 divided by 10 is going to give us 0.9 for both of these columns. Okay, last step. Sum the final column. So we ended up with 0.9 and 0.9. And remember, in our chi-squared formula, we had that sum symbol, and that means we're adding up these two numbers that we got. So 0.9 plus 0.9 equals 1.8. And that is our chi-squared value. So yay, we figured out our chi-squared. It's 1.8. The question is, what does that mean? That means nothing to us right now. Chi-squared of 1.8, what does that have to do with men and the women and the ratio? It really doesn't say anything. So we have a couple more steps that we have to do before we can actually make any conclusions. Okay, so here's what we're going to use to make sense of that 1.8 number. This is a table that looks a little ugly. It's got a lot of numbers. Maybe you're noticing that there are some decimals on the top here and some numbers on the left-hand column that are under this DF heading. So we're going to first look at what this DF means. DF stands for degrees of freedom, and I think it'll be easiest to explain what this means with an analogy instead of talking about it straight from the definition. So let's imagine that you are back at Bush. We're not remote learning anymore. And you're in a really small class that only has 5 people. And because Bush is very efficient with the number of chairs that it's putting in classrooms, your class has 5 people, and there are also 5 chairs, 1 chair per student. If you are really quick in the passing period, you don't have to go to the bathroom, you don't need water, you don't need a snack, you get to the classroom really early, you have your pick of any of these 5 chairs, right? So if you get there first, you have the freedom to pick between any of the 5 chairs. So you pick, you're free to pick, you decide on your chair. The next person who comes in also has freedom to pick. There are a lot of chairs left. They're not quite as free as you because you already took one, but they still have a lot of choices. The third person who comes in, starting to be more limited options on the chair front, but they still have choices. There's 3 chairs to pick from, and they get to choose one. Same thing with the fourth person. There's only 2 left to pick, but they're still free to pick between one of those 2. When the last person comes in, they're not free to pick because there's only 1 chair left. So that's the chair they have to take. Maybe that's the chair that's like right next to the teacher's desk or something. They aren't free to pick. They're stuck with whatever is left. So the idea is that when we're thinking about who's free or the amount of freedom that we have, it's always going to be 1 less than the number of options or categories that we have. So degrees of freedom is going to be however many categories or options we have. Here we have 5 chairs minus 1. So this would have 4 degrees of freedom in this example. Going back to our actual data set, our chairs, our options, are going to be these categories that we used to categorize our data. So here we had 2 categories, men and women. And so since we have 2 categories, we're subtracting 1, so our actual degrees of freedom is just 1. So what that means is when we're looking at this table, we're only going to be paying attention to this first row right across here, where the degrees of freedom correspond to 1. So this is the row that we're paying attention to here. If you were doing a different example and you had 3 degrees of freedom, you would only be paying attention to this third row right here. So this is nice because now we can totally ignore all the rest of these and focus just on this one, this first row across right here. Okay, so we figured out our row that we're paying attention to. Now we have to figure out our column that we're paying attention to. Which number are we actually looking at in this row? And these numbers across the top, these columns, correspond to probability levels. And if you've ever worked with p-values before, these are actually p-values. So what these p-values mean, this is going to be like a simplified explanation because you could probably take like a whole college course just on p-values. But for us, what this p-value is going to say is if the null hypothesis is true, how likely is it that we actually get the data that we got our actual data that we collected? So is there a 5% chance that if the null hypothesis was true, we would get our actual data set? Is it a 50% chance that if the null hypothesis is true, we would end up getting our actual data that we collected? Is it a 0.01? Is it a 1% chance that if our null hypothesis is true, then we would actually get the data that we got? So this is just saying, how likely is it that we get the actual data that we collected if the null hypothesis was true? Conventionally, scientists tend to use this 0.05 as the cutoff for being statistically significant. It's kind of arbitrary. There's no like special thing about 0.05. It just tends to be what we usually look at. So let's use that as our cutoff, 0.05. How likely is it using a 0.05 cutoff? So based on this 0.05 column with 1 degree of freedom, our special magical number is 3.84. So now we have 2 numbers. We have our chi-squared value of 1.8 and our cutoff number of 3.841. So the way to interpret this is to look at which side of this probability table the smaller numbers fit in on. So if we have 3.8 as our cutoff, you can see that over here on this end of the probability table, we have smaller numbers. So that means that ignoring our actual chi-squared value, if we had gotten a chi-squared value of 0.45, then it would be a 50% chance that we'd get our actual data, even if the null hypothesis was true, even if it was actually 50-50 in Biotown. So, and if we'd gotten a chi-squared value of 2.7, then there'd be a 10% chance of us getting our actual data set, even if Biotown was 50-50. So you can see our chi-squared value is 1.8. So it's falling somewhere in here, in between a 10% chance and a 50% chance that we would get our actual data set of 13 men and 7 women, even if Biotown is in actuality 50-50 men and women. So that means that it's a little bit too, we can't be very confident that Biotown is actually skewed one way or another, because it's still like kind of likely that it's decently likely that we would get our actual data just because of random variation in the amount of people that we're sampling. So what we say, if this is the case, is that we fail to reject the null hypothesis. So we can't exclude the idea that Biotown is actually 50-50, and just because of variation, we got a sample that's like a little bit skewed. So we fail to reject the null hypothesis. This doesn't say that we're accepting the null hypothesis. We're not saying like, oh yes, the mayor's right, Biotown is 50-50. We're not accepting her hypothesis. We're not accepting her claim. We're not accepting the null hypothesis. We just can't reject it. So this is like saying that somebody is found not guilty. We're not saying they're innocent. We're saying they're not guilty. If, on the other hand, our chi-squared value was over here, was really high, higher than 3.8, then this would mean that there was less than a 5% chance that we would get our data if the null hypothesis was true. And if that was the case, we would reject the null hypothesis because we're saying the chances of us getting our data if the null hypothesis was true is so small that we just like don't think that that's what's happening. So we would reject the null hypothesis if we're up here in the high numbers above our cutoff, but we fail to reject our null hypothesis if we're down below our cutoff number. So that's how our chi-squared test works. There are a couple more slides where you're going to practice, and we're going to practice more in class, but this is an introduction to the idea, which we'll be using a lot more later this semester. So I will see you guys soon.